So this is joint work, as Nir said, with Hector Geffner, my supervisor. And basically the talk is about the way in which using a more expressive language can be useful not only from a modeling point of view, but also from the computational point of view, because it might allow us to derive more informed heuristics. So as many of you know, some of the successful heuristics in recent years are based on the relaxed planning graph data structure, which is usually defined for propositional planning. Indeed, however, there is a direct generalization into non-propositional languages, which is based in what has been called the value accumulating semantics. So basically, these semantics make two key assumptions. One is that of monotonicity, in which, as you know, the number of values in every layer of the relaxed planning graph keeps increasing monotonically, and basically this allows us to ensure the tractability of the heuristic. And the other one, which is less explicit, is that of decomposition. And this basically holds that for a certain conjunction P and Q to be reachable in a layer of the relaxed planning graph, we only require that P is reachable and Q is reachable in an independent manner. The problem with this second assumption is that the resulting heuristics can be rather poor sometimes. So this is the counters domain. This is an example where these heuristics are poor. Basically here we have n integer variables taking values in a positive integer domain, and we only have actions that increase or decrease the value of every variable by 1. So say, for instance, that we have an initial situation where all variables are set to 0, and the key thing here is that we have a goal of this form. We have a goal of the form x1 is less than x2, x2 is less than x3, and so on. So under the assumption of decomposability that I mentioned before, it turns out that every one of these inequalities can be reached in the first layer, because independently every atom can be rendered true. So this means, among other things, this means that the H max value of the initial state will be 1. However, a more accurate cause would be n minus 1, because under the delete-free relaxation of the problem, one can see that if we want to reach all the goal atoms at the same time, we would actually need n minus 1 steps. So how can we do better than that? How can we have a more informed heuristic? Basically, we want to retain the assumption of monotonicity, but we want to drop the assumption of decomposition. This basically means that we won't evaluate every goal atom independently in the relaxed planning graph, in every layer of the graph, actually. But instead, we want to check if the entire conjunction or the entire formula is satisfiable by some interpretation in a certain set of logical interpretations, which, as we will see next, is directly defined by the possible values of every variable in the relaxed planning graph layer. So, for instance, in the counters domain that I mentioned, this set of logical interpretations would be directly derived from all possible assignments of values that basically assign either value 0 or 1 to every variable. And in this case, every atom, as I said, every atom can be satisfied by some interpretation in this set of interpretations, but yet there is no single interpretation that satisfies all of the atoms at the same time. So this is the outline for the rest of the talk. First, I will formalize the previous idea on a more expressive first-order language, which is functional strips. Then we will see how the usual heuristics can be generalized to this language in a much more informed manner, but unfortunately, this manner is intractable. Third point, we will see that we can approximate this generalization in a way which is polynomial, but still retains some of the accuracy of the heuristic. And we will try to show this over some empirical examples. So let me first give you a brief overview of functional strips. Basically, functional strips is a fragment, is a classical planning language which is based on a fragment of first-order logic. Basically, we get rid of quantifiers and variables, and what we have is that every functional strips planning language can be defined by these 4 elements. First, we have a set of symbols, which can be either constant, function, or predicate symbols. And we can make here the usual distinction between fluent and fixed symbols. In this case, fluent symbols are those symbols whose denotation can be changed by the execution of actions. Now, we also have a set of actions, and every action here is defined by a precondition, which is a formula over the language, and a set of effects, which are basically updates of this form here, where f is a functional symbol, t is a tuple of terms, and w is a term. So besides that, as usual, we have an initial state of a problem, and the goal of the problem will be a formula over the language. So this is a very nice slide, but we don't have much time to go over it. Basically, I wanted to show a couple of encodings of classical problems in functional strips. So this is the full encoding, and I just wanted to focus on the things highlighted in green. Basically, instead of having the usual predicates on for blocks world, I can have a log function, which obviously gives me the location of any block. And because of the power that functions give me, and because I can have complex expression like this one here, all I need is a single action, a single lifted action that can basically move any block to any place. This is a puzzle, and basically the same message holds here, because I have functions and I can have arbitrary terms and arbitrary expressions like this one here or this one here. The whole of a puzzle reduces to a single action move in a certain direction. So this basically gives rise to 4 grounded actions, which is, in a sense, much more compact than the usual propositional version. So let me give you 4 notes about the semantics of the language. Probably the basic concept in functional strips is that the concept of state variable, which is very basic. We define a state variable to be any term, any logical term of the form f of t, where f is a functional term, a functional fluent, sorry, and t is a tuple of constant fixed symbols. So as we can see here, so this is blocks world. Clear of B2 is a state variable. Location of B3 is a state variable, but clear of location of B3 is not, because this location of B3 here is not a constant fixed symbol. Indeed, this is a nested functional fluent. Okay, so based on this, we defined a functional strips state to be any assignment of values to state variables. And indeed, we can see that any FSTRIPS state determines a single logical interpretation over the language, meaning, among other things, that the value of any term or arbitrary formula can be fully determined from the value that we assign to state variables. So, enough with the language. Let me show you how we generalize the usual relaxed planning graph heuristics to this new language. As I said, this generalization to non-propositional languages is usually based on value accumulating semantics. And essentially, we have that every layer in the relaxed planning graph contains a set of reachable values for every state variable. So the key assumption, as we said before, is that the sets of every layer are going to grow monotonically, meaning that the actions that we can apply accumulate new values over the values that we already had in the previous layer. So this is an interesting observation. Basically, we can see that the sets of reachable values in every layer of the graph implicitly encode a certain set of logical interpretations over the language. So we denote this set by vk, and this set can be determined in a straightforward manner by the Cartesian product of the reachable values for every variable in the problem. Now, under this interpretation and under this observation, we can see that the standard or naive generalization of the relaxed planning graph that assumes decomposability, in this generalization, say a certain conjunction of atoms, such as the one here, is taken to be true in a certain layer, if and only if for every atom in the conjunction, we have some interpretation in this set vk here that satisfies the atom. So basically, we want an interpretation that, independent of the other interpretations, is going to satisfy every atom. But we can also define a more constrained version of the relaxed planning graph. And basically, in this version, we have that, in general, any precondition or Gore formula, any arbitrary formula, is taken to be true in a layer of the relaxed planning graph, if and only if there is a single interpretation that satisfies the whole formula in this set of, in this set v to the k that we defined. All right, so this is a very basic distinction, but basically it has a huge impact. So for instance, in the very simple counters example that I was defining before, if you recall, we had this type of goal, and basically this is the relaxed planning graph over this problem. In layer 0, we have that the only reachable values for every variable is value 0, because it is the initial state for which we are computing the relaxed planning graph. And then in this layer, we're going to be able to apply all the increase actions, meaning that we're going to accumulate a new value 1 in the set of reachable states for every variable. So now, under the standard generalization of the relaxed planning graph, we have that every atom of the form x is less than y can be satisfied in this layer as soon as we assign 0 to the variable on the left, and we assign 1 on the variable to the variable on the right. So again, this means, among other things, that the Hmax value for this state is going to be 1. But indeed, if we think on the constrained version of the relaxed planning graph that we just defined, there is in this assignment of values, there is no single interpretation that satisfies the entire goal formula at the same time. So indeed, for this more constrained version, we have to keep applying actions, and we have to keep building layers of the relaxed planning graph until we reach layer n-1, when we can see that there is indeed an assignment of values to variables that satisfies G. And in the sense, we can say that the Hmax value of this state is going to be it's going to be closer to the optimal heuristic value. So we have seen that for this constrained version of the heuristic, we have a more informed heuristic. But of course, the computation of the heuristic is NP-hard, because basically we want to search an interpretation among a set of potentially exponential set of interpretations. Now, it turns out that the basic operation in this generalization of the relaxed planning graph essentially boils down to solving a constraint satisfaction problem, which is basically the straightforward constraint satisfaction problem that we can think of. Basically, the variables of the CSP are the state variables of our planning problem. The domain of every variable in the CSP is given by the set of reachable variables in that particular graph layer. And every atom in the goal G, and here I'm assuming with a lot of loss of generality, I'm assuming a conjunction of atoms. Every atom in the conjunction is mapped into a CSP constraint that is basically defined on the state variables involved in that atom. Now, if we can map our problem into a CSP, we can also use a polynomial constraint propagation in order to relax our notion of satisfiability. And basically, this means that we can consider that a conjunction of atoms, for instance, is satisfiable in a certain layer if, after applying constraint propagation to enforce a certain notion of local consistency, no domain of our variables have become empty. This gives rise to what we call the approximate constraint relaxed planning graph, which is basically a relaxed planning graph whose construction is polynomial, but still is more informative than the standard RPG, as we will see next. And also an interesting observation is that actually any predicate in our language can be seen or can be understood as a constraint in the CSP. Basically, as long as I provide an external custom constraint propagation algorithm, I can use that to infer things much more efficiently. And in particular, this means that we can use any sort of global constraint in the definition of our problem. So for instance, this has two basic advantages. First is that we give increased expressive power to our language. So for instance, if you think of the classical blocks world, where my goal now is an all-if constraint. Basically, I want to enforce that the location of every block is different to the location of others. Basically, if you think about it, this is essentially a very compact manner of saying that I want all of my blocks to be in a single tower, regardless of the particular identities of blocks. And the second advantage that global constraints give us is that we have an increased propagation efficiency that derives from the faster propagators that global constraints have. All right, so quickly moving to the empirical results, we have implemented the previous ideas in what we call the FS0 planner that basically accepts a subset of functional strips. We're working on accepting the whole of the language, but this is a substantial subset of functional strips. Basically, we can handle a number of global constraints, but we can indeed add any global constraint in a very easy manner. And the planner basically performs a greedy best first search with a constrained version of HFF. Now, we have evaluated the planner on a few meaningful functional strips problems that basically try to highlight some of the computational advantages that we have when deriving heuristics over the language. And we compare this to equivalent propositional encodings with the FF planner. In the paper, we have also used llama and metric FF, but we only show here the results of FF. Basically, every row in the table is a different domain. So basically, the 3 domains here are variations of the counters domains that I showed to you before. And we have here other domains that I don't have time to go into, but they try to highlight different aspects of the language. And basically, we are focusing here on coverage, on plan length, the number of expanded nodes, and the time and the overall time. So in general, the numbers are pretty good for our planner. And the basic message is that the constrained version of the heuristic is rather more expensive to compute, but the increased accuracy of the heuristic compensates this in terms of coverage, length, and expansions. So even in time, sometimes we have better times. Sometimes FF has, of course, much better times. So for instance, it's interesting to notice that, for instance, in plan length, sometimes we get plans which are, on average, 5 to 10 times shorter than the ones which are output by FF, meaning that our heuristic guides the search in a much better manner. So, okay, basically, let me highlight the 3 main contributions of the work. First, we have provided a logical analysis of the relaxed planning graph that allows us to see that, or to identify a general weakness of the relaxed planning graph, which actually gets hidden when we use propositional languages, but comes to the surface as soon as we move into more expressive languages that feature multi-valued variables. So based on that, we have defined a stronger version of the heuristic for these more expressive languages, but unfortunately, it wasn't tractable. But we have also seen that based on constraint satisfaction techniques, we can obtain a relaxed, so an even more relaxed approximation, which indeed is polynomial, and it turns out that it is more informed than the standard relaxation. And we have implemented these ideas on the FS0 planner, as I said before. And basically, if I had to highlight a single take-home message, is that we have provided some empirical evidence that the expressiveness of a language and the computational efficiency with which we can reason within this language are not necessarily in conflict. So we have seen, for instance, that with functional strips, a more expressive language is able to capture the structure of the planning of the planning problem in a manner which is more suitable for the heuristics to be derived. That's pretty much everything. Thank you.